Hi everybody, this is a quick overview on nitration. That's going to be an aromatic substitution of a hydrogen for a nitro group. Here's your basic reaction. You've got benzene plus nitric acid has to be run in the presence of sulfuric acid, and it's going to produce a nitrobenzene and a water. Now let me help you look at this to make sure that you understand it. If I rewrite nitric acid as OH-NO2, there's your nitro group. And we know that there's understood to be a hydrogen right here on this benzene. It could be any hydrogen, okay? I'm just picking this one for convention out of habit. The nitro group is going to substitute. It switches places. It's going to substitute that hydrogen. And then you get the nitrobenzene. That nitro attaches to the benzene ring, that aromatic. You then have HOH, right? The H and the nitro replace each other. HOH, which is just water. Nice. So the couple of takeaways on this. For a nitration reaction is going to be the benzene, that's your aromatic, plus the nitric acid, and it's going to produce that nitro group, and so it will produce the nitrobenzene. Again, if you're doing flashcards, make sure you write down sulfuric acid. It has to be run in the presence of sulfuric acid. Now, some examples. I'm going to lay a foundation and build my way to giving a pretty cool example with sulfa drugs. Nitro groups can easily be converted to amine groups. Here is an example. I can take that nitrobenzene, going to add hydrogen to it, run it in the presence of a metal catalyst. So there's the palladium, and it's going to produce aniline. It's going to be the benzene with the amine group, that NH2 on it. Pretty cool. Now, the aniline, this amine on the benzene, we use those in sulfa drugs. There's a category, family of drugs called sulfa drugs. They're antibacterial. A couple of things about this. We'll use them often to treat like ear infections or UTIs, urinary tract infections. The first sulfa drug was synthesized in the 1930s, and it was called sulfanilamide. Sulfanilamide. Now, significance, how this works, the mechanism of how this antibacterial works. Well, microorganisms, they make folic acid inside of themselves. And the way they do that, they get folic acid from the synthesis of a compound called para-aminobenzoic acid, okay? So inside the organisms, they're going to synthesize folic acid by changing para-aminobenzoic acid into the folic acid. Well, this para-aminobenzoic acid and the sulfanilamide are very, very similar in size, shape, and function. So when a person takes the sulfanilamide, the bacteria, and it's going to be any bacteria in their body, but we're focusing on getting rid of that bad bacteria, that bacteria is going to uptake the sulfanilamide thinking it can use that to synthesize folic acid. Well, it's a trick. It can't synthesize folic acid from the sulfanilamide, which makes the bacteria so it can't reproduce, and then it dies. It's going to completely derail the process. It can't make the folic acid, so it dies. Now, what's great about this is the bacteria will synthesize folic acid, but humans can't synthesize folic acid. We have to get our folic acid from consumption by eating, in particular, like leafy greens are going to give us our folic acid. So this trick of the sulfanilamide, it only works for the bacteria. It's going to be safe for humans. Pretty cool. All right, nice. If this was helpful, hit that like button. Thank you for being here. It's a pleasure. Have a good day. Bye.